Something inside Comet 3I Atlas appears to be blocking light, and by normal comet physics, it should not be there. The high-contrast image that began circulating online in late 2024 looks wrong the moment you see it. In the bright coma, the luminous cloud around the nucleus, there is a dark wedge with a coherent outline. It is not a soft dimming or a random noisy patch. It reads as a structured void cutting through material that should be irregular and diffuse. Comets are not orderly systems. As sunlight warms their surfaces, ices sublimate and drive gas jets outward. Dust grains are carried in those jets, tumbling, colliding, and spreading into streamers. The solar wind pushes the tail away from the sun, and magnetic interactions can disconnect whole sections of the ion tail and send them spiraling off. The result is a turbulent environment that changes hour by hour. In that setting, a stable shadow with recognizable geometry is difficult to explain. The story behind the image is unusual in a practical way. Amateur observers say they started from standard public FITS frames, stacked them to improve signal, removed background stars, and pushed contrast far beyond what official releases normally show. During that aggressive processing, the dark sector emerged. What matters is that the feature did not appear in just one frame. Multiple independent people processed different sets of exposures taken on different nights and kept seeing the same basic wedge. The shadow was still there hours later, still there on later stacks, shifting slightly but maintaining its overall shape. That repeatability makes simple glitches, like a hot pixel or a single cosmic ray hit, an unlikely explanation. Naturally, the first question is whether a comet can generate something like this without invoking anything exotic. There are real effects that can make parts of a coma look darker. Phase angle geometry can reduce brightness in certain directions depending on where Earth sits relative to the Sun and the comet. Projection along our line of sight can create misleading shapes that exist only from our perspective. And dust jets on the night side of a rotating nucleus can carve low-density cones into the coma, producing subtle shadows in the dust distribution. Those mechanisms are all known. The problem is their scale and stability. In typical comets, these shadows are faint. You see them only after careful modelling of dust density, and their boundaries are soft because the coma is a moving, diffusing medium. They do not create stark black regions in a pushed contrast image. They do not hold a similar geometry over multiple observations as the comet rotates and viewing angles change. So while the models can explain mild dimming, they struggle with a wedge that looks both deep and persistent. If the dark region is real, two broad explanations remain. The first is a genuine void, a zone with far fewer scattering particles than the surrounding coma. But then we have to explain how a void stays empty inside turbulence. Typical comet dust ranges from nanometers to millimeters in size and scatters sunlight efficiently. That scattering is why comets are visible at all. To create a pronounced darkness, you would need an almost total absence of grains along our line of sight, sustained over time. In an outflow that is continuously replenished, that is a tall order. A low-density region should refill or distort quickly unless there is a stable physical cause to keep it clear. The second explanation is Occultation, something opaque blocking light before it reaches us. In other words, a solid structure casting a shadow. The geometry problem becomes straightforward. Place a dense object between a bright region and the observer, and a wedge of darkness appears behind it. The uncomfortable part is that comets do not normally host large, coherent, solid bodies embedded in their tails. Yes, comets sometimes fragment. A chunk can break off and travel nearby. But fragments usually show up as additional bright condensations, almost like small companion comets with their own mini-comae. They do not typically create an empty sector, and in the reported stacks of 3I Atlas, the shadow seems to hold a position relative to the nucleus rather than drifting away as a loose fragment would under the same outgassing forces. At this stage, skepticism focuses on the reduction pipeline. High contrast processing can manufacture features if star subtraction is too aggressive, if background gradients are removed incorrectly, or if a bright star passing behind the coma is mishandled. Astronomy has a long history of apparent anomalies that vanished after careful reprocessing. That caution is justified, and no peer-reviewed paper has yet confirmed a solid object. All we can say with confidence is that multiple observers keep retrieving some version of the same dark wedge from independent datasets. That is enough to label it an anomaly worth studying, not enough to declare what caused it. The broader context adds pressure because 3I Atlas is an interstellar object. It is only the third body we have clearly identified as arriving from outside the solar system. The first, Oumuamua, in 2017, triggered years of debate because its light curve implied an extreme shape, and because it experienced small non-gravitational acceleration during departure. Many natural models were proposed, and an artificial light sail idea was argued but never confirmed. The second 2I Borisov, in 2019, looked like a normal comet at first, then turned out to have chemistry that did not match solar system comets. Now the third arrival shows a visual feature that our standard comet models do not predict. That sequence could be coincidence, or it could be a hint that interstellar bodies are simply more diverse than what formed here. Compared to Oumuamua, this is less dependent on subtle inference and more about something you can point to in an image. If the shadow is authentic, it signals either an unfamiliar natural mechanism in interstellar comets or a physical structure within the coma that we have not previously encountered. Either way, the scientific stakes are high, and so is the reputational risk. Make a dramatic claim too early, and you become the person who announced a discovery that evaporated. Stay silent too long, and you invite the suspicion that something is being withheld. That tension is part of why the public conversation is moving faster than the formal one. So we are left in a narrow corridor between two possibilities. The shadow could still be an artifact, and history says that is often the correct answer. But if it is not, then we may be looking at the first clear visual clue that interstellar objects can behave in ways that are not just different, but structurally unexpected. The obvious next step is to stop treating the image in isolation and look at the comet's motion. If something unusual is present in the coma, it may also show up in the trajectory through small deviations from a purely gravitational path. That is where the discussion has to go next, because a strange shape in the tail is intriguing, but a strange path through the solar system is measurable, testable, and far harder to dismiss. Avi Loeb has a knack for making the scientific room go quiet. The Harvard astronomer spent years arguing that Oumuamua might have been technological, and that history is impossible to separate from what he says next about Comet 3I Atlas. His new paper centers on a number that spread fast, 0.05%. That is his team's estimate for how often an interstellar object would naturally end up on a trajectory like this one if such visitors arrive from random directions at random speeds. In their simulations, out of 10,000 hypothetical interstellar pass-throughs, only about 5 follow a path. This well aligned for a close encounter with Jupiter and a deep pass through the inner solar system. Loeb's point is not that the number proves design. His point is that the geometry looks unusually useful, the way a planned route looks useful to an engineer. Critics immediately circled the assumptions. The math is straightforward, but the priors are not. We have only 3 clearly confirmed interstellar objects, so we don't know their true population, their preferred directions, or their speed distribution. If interstellar debris tends to travel in galactic streams or comes disproportionately from certain regions, then a trajectory that looks extremely rare under a random arrivals model might be far less rare in reality. This is where Bayesian reasoning matters. Your confidence depends on what you assumed before you opened the data. If you start from the belief that alien technology is effectively impossible, then even a 1 in 20,000 natural orbit feels more plausible than an artificial explanation. If you start from the belief that advanced civilizations could send probes, then the same number becomes a reason to investigate the technological hypothesis more seriously. The probability does not settle the question. It tells you how odd the orbit is under specific starting assumptions, and it forces the community to argue about what those assumptions should be. Set the probability debate aside and look at what 3I Atlas is doing in plane orbital mechanics. The comet arrived on a hyperbolic path, meaning it came from interstellar space, and, without additional forces, would keep going back out. But its incoming trajectory is arranged to pass close enough to Jupiter for the planet to significantly alter its speed and direction. Jupiter is the only body in the solar system massive enough to do that to a fast interstellar intruder. If any natural or artificial process were going to reshape this orbit, Jupiter is where it would happen. We use gravity assists all the time, usually to speed spacecraft up. A probe falls toward a planet, swings around it, and leaves with extra velocity. Voyager, Cassini, and New Horizons all relied on that trick. The same basic physics can be reversed. If you approach from the right direction, the planet pulls against your motion and steals momentum instead of adding it. You arrive fast and leave slower. This is gravitational braking, a way to shed speed without carrying a huge fuel load. Loeb and his co-authors argue that 3I Atlas is set up for exactly this kind of braking encounter. If that were happening, you would expect tiny deviations from a pure gravity-only orbit. A strictly Keplerian path is smooth and predictable. A controlled braking approach would need small course corrections to keep the geometry precise, because the timing at Jupiter has to be right. According to current orbital fits, 3i Atlas does show non-gravitational acceleration terms, additional forces beyond simple gravity that are required to match the observed positions. Non-gravitational acceleration is not rare in comets. Outgassing can act like a set of weak, messy thrusters. As different patches of ice warm and sublimate, jets of gas push the nucleus slightly. In most comets, those forces change as the body rotates and as surface activity evolves. The acceleration direction wanders. The magnitude varies. If 3i Atlas were behaving like a normal comet, any lucky alignment with Jupiter's braking geometry would be intermittent and accidental. What makes this case controversial is the claim that the acceleration looks organized. Its direction appears to line up with the adjustments you would want if you were aiming for a particular Jupiter encounter. Random outgassing can change an orbit, but it does not optimize it. Station keeping does. The idea is that the comet's deviations from a gravity-only prediction follow a consistent pattern, like repeated nudges in the same strategic direction. Amateur astrometry has become part of the evidence stream. Modern backyard observers with good CCD cameras and careful reduction techniques are tracking 3i Atlas night after night. Several groups report that the comet's actual positions drift from clean, gravity-only ephemerides in a way that is coherent across independent measurements. Professionals are right to be cautious here. Small systematic errors can mimic patterns, and extraordinary claims require extraordinary calibration. Still, amateur networks have matured. They share methods, cross-check each other, and in some cases produce astrometry close to professional quality. Their advantage is speed and persistence. They can follow an object intensively, while big observatories are constrained by scheduling and bureaucracy. If the acceleration is real and sustained, the next question is how much force it implies. Changing an orbit by the reported amount requires a certain total impulse. Outgassing can supply that only if the comet loses enough mass in roughly the right direction for long enough. That should leave fingerprints. Strong jets should be visible. Brightness should vary more dramatically. Spectra should show unusually vigorous volatile release. Yet 3i Atlas looks like a comet that is active, yes, but not outrageously so. There is gas and dust, but not at a level that obviously matches the acceleration budget. Some weak jet-like features have been seen, and it is possible that crucial outgassing is happening on the far side of the nucleus or in ways we have not modelled well. It is also possible that the acceleration is being overestimated because the orbit fits are still young and sensitive to noise. None of this is settled, but the mismatch is one reason some researchers refuse to dismiss the technological scenario out of hand. You need a mechanism that can push this object in a specific direction without loudly advertising itself in the coma. If Jupiter braking is the goal, what comes after the flyby matters. A successful braking encounter could reduce the object's speed enough to shift it from an unbound interstellar pass to a bound solar orbit. In plain terms, it could park in our system. Parking in space does not mean stopping, it means settling into a stable or semi-stable trajectory that can persist for a long time with little correction. The solar system has several such niches. The Trojan regions 60 degrees ahead of and behind Jupiter are gravitationally stable and crowded with small bodies. A high inclination orbit, steeply tilted relative to the ecliptic, can remain stable for long periods and offers a wide observing vantage. Resonant heliocentric orbits, where periods lock into simple ratios with Jupiter's, can also be long-lasting. Why would anything park here? The conservative answer is that nothing is parking. The comet might be passing through, and the Jupiter encounter could be coincidence amplified by our tiny sample size. But if the orbit and acceleration are coordinated, parking becomes a natural mission objective. A parked probe could observe the inner solar system over thousands or millions of years, monitoring planets, watching for signs of life or technology, or acting as a waypoint for a larger network. Those are speculative interpretations, but the mechanics behind them are not exotic. Gravity assists and braking are standard tools in our own spaceflight. The open question is whether we are seeing a natural comet that happens to line up with those tools, or an object using them deliberately. So the case now rests on three linked anomalies: a shadow in the coma that might imply solid structure, a trajectory that looks statistically odd under some models, and non-gravitational acceleration that seems aligned with a Jovian braking approach. None of these pieces is decisive alone. Together they form a pattern that is hard to ignore and easy to overread. The only way forward is more data, especially high-contrast imaging, infrared constraints, and precise astrometry as Jupiter draw near. Because whatever Three-Eye Atlas truly is, the 2025 encounter is the moment when the geometry stops being hypothetical and turns into an observable test. If we take the orbital anomaly seriously, the shadow stops being a curiosity and becomes part of the same puzzle. You now have an object that seems to be adjusting its path, yet it does not look active enough to explain that adjustment by normal comet outgassing. That mismatch forces a hard question. What kind of structure could sit inside a cometary coma, cast a coherent shadow, and possibly contribute to controlled acceleration? Start with the simplest structural idea: a shield. If a solid body is embedded in the inner coma, positioned between the nucleus and part of the dust cloud, it could block scattered sunlight and create a wedge of darkness behind it. The geometry in the processed images is consistent with something that is not spherical. A shield-like shape would naturally cast a sector-shaped shadow depending on how it is oriented relative to the Sun and to Earth. But the moment you place a solid structure near the Sun, you run into heat. Sunlight at Earth's distance delivers about 1,300 watts per square meter. Closer in, the flux rises sharply. Any dense object sitting in direct sunlight will absorb energy and warm rapidly unless it can radiate that heat away. A bare rock can handle high temperatures, but ice cannot. If the shadowing structure were mostly ice, it should sublimate, erode, and blur out fast. If it were metal or a refractory material, it might survive, but then another question appears. How did a large coherent chunk of that material end up outside the nucleus and still remain close enough to it to cast a stable shadow? That thermal constraint leads to a second structural possibility. Maybe the object casting the shadow is not a shield but a radiator. Spacecraft generate waste heat. Electronics, power systems, and internal machinery all produce it. In vacuum, there is only one way to get rid of that energy: radiate it away. That requires surface area. A radiator panel would be extended, relatively flat, and deliberately oriented to dump heat into cold space. Such a panel could cast a clean geometric shadow inside a glowing coma. A radiator idea also fits the timing. If the object is performing a braking or parking maneuver, it is dealing with a large energy problem. Arriving from interstellar space means arriving fast. Even if Jupiter's gravity does most of the braking, the object still needs some thruster-like control to refine the encounter. That control costs energy. If there is any active system at work, heat is a byproduct, and heat must be managed. A radiator would be functional, not decorative. Thermal modelling makes this line of reasoning sharper. At distances of roughly 3 to 4 astronomical units from the Sun, cometary brightness is dominated by scattering from ice grains. As the comet moves inward and those grains sublimate, dust and refractory materials, silicates and organics take over. If a solid structure is present, its thermal and infrared signature should change with distance and composition. A metal panel would glow in infrared differently from ice or rock. So far, infrared data do not show an obvious excess. The object radiates broadly like a comet. But infrared observations are hard to interpret when a small structure sits inside a bright, evolving coma. A weak or narrow thermal signature could be hidden in the noise. There is a third family of structural ideas tied directly to propulsion. If you want to steer without carrying fuel for millions of years, you look for passive or low fuel systems. One example is a magnetic sail. A magnetic sail uses a strong magnetic field to interact with charged particles in the solar wind, generating thrust. It requires no propellant, but it does require a large field structure produced by superconducting coils. The thrust is weak, the timescales are long, and the structure must be extended enough to couple to the wind. If something like that were deployed inside the coma, it could alter plasma and dust densities unevenly, potentially producing a shadow-like void. We already know that natural comets interact with magnetic fields. Ion tails align with the solar wind. Disconnection events happen when field lines snap and reconfigure. An engineered magnetic interaction is speculative, but the physics itself is not exotic. It takes a natural phenomenon and pushes it under control. That could, in principle, link the shadow in the coma to the organized non-gravitational acceleration in the orbit. A fourth idea is simpler and, in some ways, more elegant. Trim systems. Think of trim vanes as small panels or surfaces that can be angled to produce gentle but persistent forces. They can exploit solar radiation pressure or drag in a gas flow. If you had a long-duration probe, you might prefer passive steering to active thrusters. Orient a surface, let sunlight push, and you get a slow directional correction. A trim system could also cast a shadow depending on its orientation and size. It would not need to be huge to matter over long timescales, only consistent. All of these structural hypotheses face the same survival problem. An object that has crossed interstellar space has endured thousands to millions of years of radiation, micrometeorite, impacts, and thermal cycling. Then it arrives at a star system and enters a far harsher environment. Near the Sun, temperature swings can span hundreds of Kelvin between sunlight and shadow. Cosmic rays slowly damage materials. Small impacts chip away at exposed surfaces. Any artificial structure would need to be exceptionally robust, redundant, or both. The fact that the shadow remains coherent across multiple observations suggests either a rigid attachment to the nucleus or active stabilization to keep orientation steady. A tumbling, flexible apparatus would likely produce a shadow that shifts more chaotically than what observers report. At the same time, scientific caution has to stay in the foreground. No peer-reviewed paper has confirmed that the shadow comes from a solid artifact. We have images, we have repeated retrievals of the feature under high contrast processing, and we have plausible physical arguments that it is hard to explain naturally, but the interpretation is still open. In astronomy, a surprising image is not enough. You need converging evidence from different instruments, wavelengths, and reduction teams. Even with that caution, the social reality matters because this is happening in public, in real time. In the old model of science, raw data lived inside institutions. Analyses were slow. Results arrived as papers. Today, the data are often public within days, and so is the debate. If big observatories clamp down too hard on preliminary releases, they risk looking like they are hiding something. If they release unvetted high-contrast images, they risk fueling a false alarm. Either way, the credibility cost is real. That is why the silence from major facilities has become part of the story. When a genuinely interesting object appears, the professional system usually swarms it. Observing proposals get expedited, follow-up campaigns kick into motion, and official imagery drops fast. With 3i Atlas, most of the striking high-contrast views are coming from amateur networks and non-standard pipelines. Official statements, when they exist, are cautious to the point of emptiness. We are analyzing the data. No conclusions at this time. That is a defensible position. It is also the exact tone that makes people suspect internal disagreement. We know the big instruments are capable of seeing this object clearly. Space-based observatories watching the inner solar system, solar wind missions designed to image comets near the Sun, and even spacecraft traveling toward Jupiter all have cameras that could capture high-resolution, high-contrast data. It is hard to believe that none of them have taken a close look. The question is not whether data exist. The question is why we are not seeing the versions that would settle the shadow debate. The most conservative answer is routine delay, calibration, internal review, competing priorities. The more unsettling answer is that teams are divided and no one wants to be the person who either shouted alien too early or ignored a genuine anomaly. Both answers are compatible with what we observe. But the longer the gap persists, the more it becomes its own signal, because absence of clarity invites narrative. So at this point the puzzle has expanded. The shadow may indicate structure. The orbit may indicate control. The thermal and survival constraints narrow what kinds of structures are even plausible. And the institutional quiet around the best data adds a sociological layer that is hard to separate from the physics. If 3i Atlas is perfectly natural, a careful investigation will teach us something new about interstellar comets. If it is not, then the way we discover that fact may matter almost as much as the fact itself. And the window for finding out is not indefinite. The object is moving on. The Jupiter encounter is approaching. Whatever happens next will either sharpen the anomaly into something real or dissolve it into another instructive false start. The investigation gets sharper when we stop asking what the object might be and ask what the object must do next. If 3i Atlas is purely natural, its near-term behavior should follow familiar comet rules. Activity rising smoothly as it approaches the Sun, dust and gas jets shifting with rotation, and a trajectory that matches a standard non-gravitational model tied to outgassing. If something more deliberate is happening, the coming months create a narrow test window. You cannot keep a controlled approach subtle forever when you pass a giant planet at close range. Jupiter is not just a large mass on a convenient path. It is a violent environment, intense radiation belts, a huge magnetosphere, and a complex gravitational field. A small body flying through that region experiences tides, heating, and plasma interactions that can reshape a coma. Comet Shoemaker-Levy 9 demonstrated the extreme case in 1992, 1994, when Jupiter's tides tore it into a chain of fragments and then pulled them into collision. 3i Atlas is not following the same path, and there is no expectation of a catastrophic breakup. But the lesson is that a Jovian flyby is not a gentle cruise past a passive waypoint. It is a stress test. If the dark wedge in the coma is a real physical shadow, it should respond to that stress. A natural void carved by jets should shear, blur, or rotate as the outflow changes under new thermal conditions. A shadow cast by a coherent object should do something else. It should either keep its geometry because the structure is rigidly anchored, or it should change in a way consistent with controlled reorientation. Either outcome is informative. Even a disappearance matters. If the wedge vanishes precisely as Jupiter's environment intensifies, that would argue for a subtle natural phenomenon that collapses under stronger turbulence. If it persists with similar boundaries, that sharply raises the bar for natural explanations. The orbital side of the test is even cleaner. Right now, the non-gravitational terms are inferred from early tracking. Those terms are sensitive to noise, and the fit can evolve as more data flow in. But as the comet approaches Jupiter, the dynamical lever arm grows. Small forces applied early produce measurable differences later. By the time of closest approach, the uncertainty narrows enough that the direction and magnitude of any extra acceleration can be compared against standard outgassing models. A normal comet is messy in a predictable way. Outgassing thrust tends to align roughly away from the Sun because that is where heating is strongest. It tends to change as the nucleus rotates, and it tends to correlate with brightness changes. If the acceleration in 3i Atlas continues to point in a stable, strategically useful direction, and if it does so without a matching rise in visible activity, that mismatch becomes harder to wave away. In other words, the next phase is not about whether the orbit looks odd, It is about whether the orbit behaves like a physical engine or like a hot rotating ice rock. There is another subtle signature in the approach geometry: timing. Gravity-assist outcomes depend strongly on where the object passes relative to Jupiter's velocity vector. A difference of a few thousand kilometers in the B-plane can change the post-encounter speed by kilometers per second. An uncontrolled comet can drift into different B-plane corridors, depending on how its jets happen to fire. A controlled object aims for a corridor. If later astrometry shows that 3I Atlas is threading the needle into a narrow, high-leverage corridor that would be statistically unlikely for random outgassing, that is a real constraint on all interpretations. Now consider the energy story again, because the Jupiter maneuver is where energy choices become visible. A natural interstellar comet has only one energy strategy. It carries its kinetic energy through the system and leaves. It can lose some energy to outgassing, but that loss is small relative to interstellar speeds. A parking or braking strategy is different. It aims to transfer energy to Jupiter and the Sun-planet system, reducing the object's hyperbolic excess. That transfer can be done passively by selecting the correct inbound asymptote. But selecting that inbound asymptote requires that the object arrived already aligned or corrected itself over long time spans. If we accept the controlled approach hypothesis for a moment, the strange question becomes, why now? Why reveal any anomaly in a bright coma where amateurs can see it? The uncomfortable answer is that the anomaly may not be a reveal at all. It may be a byproduct. If the object is using some structure to manage heat, propulsion, or orientation, that structure could become visible only once cometary activity turns on. A buried apparatus could remain hidden in cold interstellar space and then emerge as dust and gas surround it, making its shadow detectable. In that framing, the cometary appearance is camouflaged by circumstance, not by design. A competing natural framing reaches the opposite conclusion. Interstellar comets may have internal structures we have never seen because we rarely observe them this close and this early. In the solar system, many nuclei are layered, fractured, and riddled with cavities. When activity turns on, those cavities can vent in ways that look engineered from a distance. Narrow cones, stable fans, temporarily coherent low-density regions. Under this view, the wedge is an accident of geometry and a reminder that even ordinary comet physics is far richer than the simplified pictures we carry around. The only way to sort those framings is multi-wavelength observation. Dust scattering dominates optical images. Gas emission dominates in specific narrow bands. Thermal behavior dominates in infrared. If the wedge is a dust void, it should show up differently in gas traces than in broadband optical light. If it is a real shadow cast by an opaque structure, it should appear consistently across dust-dominated bands, but not necessarily in gas emission, because gas does not scatter like dust. If it is a processing artifact, it should collapse under different reductions and different instruments. Convergence across wavelengths is the fastest way to kill a false signal or confirm a real one. Polarimetry can help too. Dust grains polarize light depending on size, shape, and scattering angle. A true void would alter polarization patterns in a specific way. A shadow from an object would alter intensity without necessarily producing the same polarization shift. This is niche work, but it is exactly the kind of niche work that turns a viral image into a physical diagnosis. There is also a timing constraint no one can ignore. Geometry changes quickly. The Sun-Comet-Earth angle shifts as all three bodies move. If the wedge is tied to a real three-dimensional structure, its projected shape should evolve with that changing angle. A stable projected wedge across a wide swing in phase angle would imply a highly symmetric or actively oriented physical cause. A wedge that rotates exactly as a projection model predicts would argue for a natural jet-carved void. Either outcome is measurable. This is where the third interstellar object argument becomes dangerous, because humans are pattern makers. 3 is the minimum number that feels like a trend. We want a storyline. First object weird shape, second object weird chemistry, third object weird shadow. But 3 is also the smallest sample size that can fool you. Nature can throw 3 weird dice in a row without implying anything deeper. The honest scientific posture is to keep both possibilities alive. Maybe interstellar visitors are inherently more diverse, and maybe we are over-interpreting a tiny data set. The purpose of the Jupiter season is to push this from a story into a set of constraints. If the object exits Jupiter's neighborhood still on a strongly hyperbolic orbit, still accelerating only in ways that match outgassing, and with the wedge fading into normal comet morphologies, the controversial reading will lose traction. It will not disappear completely, because uncertainty never does, but it will shrink into the category of interesting natural cases. If instead the trajectory bends toward a bound orbit, or the acceleration stays coherent without commensurate activity, or the shadow remains sharply geometric through conditions that should destroy a natural void, then the conversation changes. The burden of proof shifts. Not to aliens, but to something about this object is not covered by our current natural models. The next chapter has to follow that shift. To talk about what a bound outcome would look like and where a parked interstellar object could plausibly settle, we need to map the actual post-encounter orbital corridors. Those corridors are specific. They depend on the exact B-plane passage, the comet's spin-driven jets, and the solar gravitational field. Once those parameters tighten, we can outline which futures are physically available to this object and which are not. That is where speculation ends and a real dynamical forecast begins. To understand what parking could mean in a measurable way, we need to look at the actual orbital corridors Jupiter can place an incoming interstellar body into. This is not a vague idea. Gravity assist outcomes fall into families that dynamical models can map precisely once the flyby geometry is known. The key variable is the B-plane trajectory, the comet's path relative to Jupiter's position and motion at closest approach. Move that path slightly, and the post-encounter orbit shifts from a clean escape to a captured, long-lived solar orbit. In a simple picture, there are 3 broad outcomes. First, the comet remains unbound. Jupiter bends the path, but the hyperbolic excess speed stays positive, so the object leaves the solar system on a new outbound trajectory. This is what we expect for most interstellar comets. Second, the comet becomes loosely bound. Its speed after the encounter drops just below escape, producing a very long stretched orbit around the Sun with a period of thousands to tens of thousands of years. Third, the comet enters a resonance or niche where gravitational interactions keep it in a relatively stable configuration for much longer, potentially in a way that repeatedly brings it near planets. The resonance option is where the probe narrative finds room, because it creates useful observation patterns. A body in a resonant orbit with Jupiter can return to the inner solar system on a predictable schedule. A body in a high inclination orbit can sweep over the solar system like a surveillance camera, getting a full three-dimensional view over time. A body captured into a Trojan region leading or trailing Jupiter by about 60 degrees can remain there for extremely long durations with minimal corrections. These regions are not hypothetical. We already observe thousands of Trojan asteroids, and the dynamical stability of those Lagrange zones is routine celestial mechanics. However, capture into a Trojan state from an interstellar inbound trajectory is hard to do naturally. The Trojan zones are stable, but getting into them requires arriving with the right energy and phase relative to Jupiter's orbit. In natural capture scenarios, small bodies tend to get trapped there during the early chaotic evolution of a planetary system, not through a single clean flyby. That does not make Trojan capture impossible, but it makes it a discriminating test. If post-encounter fits push 3I Atlas toward a Trojan-like corridor, that is a dynamical oddity that would demand explanation. A high-inclination bound orbit is less restrictive. Jupiter can, in principle, pump inclinations through scattering, especially for an object that grazes its Hill sphere at interstellar speed. But the price is instability. Many such orbits remain bound only temporarily. Over time they diffuse and either crash inward or escape again. For a natural comet, temporary capture would not be shocking. Interstellar objects can be caught for a while as gravitational billiards sends them into complicated loops. The question is whether the capture, if it happens, looks accidental or looks engineered. Accidental capture has a statistical fingerprint. It is messy. The resulting orbit tends to be sensitive to small uncertainties in the inbound state and to random outgassing. When you run a Monte Carlo swarm of inbound solutions, the swarm fans out into a broad set of post-encounter outcomes. Engineered capture, by contrast, is narrow. If controlled corrections are being applied to hit a specific corridor, the swarm collapses into a tight family with a shared goal. The width of that family, relative to the inbound uncertainty, is measurable. This is where the current orbital debate becomes practical rather than philosophical. If you want to test the organized acceleration idea, you don't need to read motives. You look at the covariance. You ask whether the non-gravitational terms reduce or increase uncertainty in a way consistent with targeting. Targeting would mean the orbit solutions converge toward a narrow B-plane passage as the comet approaches rather than diverge. A normal comet under outgassing noise should not do that. The more activity you have, the noisier your path becomes. Convergence in the presence of thrust-like forces is a signature of control. There is also a time symmetry test. Natural outgassing is strongest near perihelion and fades with distance. If the non-gravitational acceleration acts like a real jet system, it could remain coherent even when solar heating is weaker, because it would not depend on sublimation. That gives you two clean epochs to compare: pre-perihelion and post-perihelion. If the acceleration pattern before Jupiter echoes itself after perihelion in magnitude and direction, despite a different thermal regime that points away from pure outgassing. If it weakens or changes direction in lockstep with observed activity, that points toward natural comet physics. Now fold the shadow back into this. If there is a structure inside the coma, and if that structure is functional, the flyby could reveal it in two ways. First, by geometry. As the comet's phase angle shifts, the projected shadow should move or rotate predictably if it is tied to a rigid element. Second, by survivability. A real solid structure should either persist through the Jovian stress without turning into a fuzzy smear, or fail in a coherent way, fracture, detach or collapse into visible fragments. A natural void, on the other hand, should degrade smoothly as the coma reorganizes. The difference between sudden structural failure and smooth morphological evolution is observationally distinct. None of this requires us to assume intent. This is important because intent is the hardest thing to infer in science. You can measure paths, brightness, polarization, spectra, and dust dynamics. You cannot directly measure the motives of an object. The cleanest way to keep the discussion scientific is to treat technology as a hypothesis about forces and structures, not about aliens. The question becomes, do we see force patterns and material behaviors that exceed the natural model space? If the answer is no, the extraordinary story collapses. If the answer is yes, a new category of object has to be considered, even if we refuse to name it yet. There is one more subtle corridor worth mentioning: quasi-satellite states. Under certain geometries, a body can enter a heliocentric orbit that keeps it near a planet for a period of years or decades without being gravitationally bound as a true moon. It loops around the Sun but appears in a rotating frame to orbit the planet. Jupiter hosts such objects occasionally. A quasi-satellite state for 3I Atlas would be dynamically rare and observationally loud because it would keep returning near Jupiter's neighborhood and remain trackable. It would also be a plausible intermediate step for controlled capture, not a permanent Trojan, but a stable holding pattern that allows further adjustments later. As the comet approaches the flyby, modelers will begin to publish corridor maps. What ranges of inbound solutions yield which outbound states? Those maps will not settle the debate on their own, but they will shrink the space where speculation can hide. If the outbound family is broad and unremarkable, the technological narrative loses oxygen. If the outbound family folds into a tight, high-utility niche, then even strict naturalists will have to propose new dynamics or new internal physics to match it. That brings us to the core principle of this entire story. The solar system is not a stage where we passively watch visitors. We have a set of gravitational gates, Jupiter being the most powerful, and those gates amplify whatever the visitor is. A normal comet enters, gets bent, and leaves. A fragile one enters, breaks apart, and leaves debris. A controlled one enters, uses the gate, and stays. The gate does not make the visitor artificial, but it makes the visitor legible, because gates convert tiny differences into visible outcomes. So when the Jupiter season ends, we will not just know where 3i Atlas went, we will know which futures were dynamically accessible to it and which future it chose in practice. That distinction matters. It is the closest thing orbital mechanics can give us to a behavioral signature. And once we have that signature, we can return to the earlier anomalies: shadow, acceleration, thermal behavior, with a new hierarchy of plausibility. Some explanations will collapse, others will harden. That is when the story stops being a viral mystery and becomes a well-posed scientific problem with a finite set of answers. If there is one place where the debate can be forced into hard evidence, it is spectroscopy. Images can mislead. Orbits can be noisy, but chemistry is stubborn. The gases and dust released by a comet are a direct probe of what the object is made of, and for interstellar bodies, composition is the fastest way to learn whether we are dealing with something simply unfamiliar or something fundamentally out of family. In solar system comets, we have a baseline chemical profile. Water dominates near the Sun. Carbon monoxide and carbon dioxide can dominate farther out. Typical spectra show CN, C2, C3, NH2, and a range of organic and sulfur compounds. The ratio between these volatiles varies from comet to comet, but it varies within a known envelope. That envelope reflects the conditions of the early solar system and the processing comets undergo as they make repeated passes near the Sun. Interstellar comets give us a chance to compare envelopes. 2I Borisov already showed that the comparison matters. Its CO abundance relative to water was higher than in most solar system comets, and it displayed a chemical pattern that suggested formation in a colder environment. It still looked like a comet. It still followed comet chemistry, but it did not fit neatly into the solar system distribution. So the question for 3i Atlas is not, does it have water or CO, because it almost certainly does. The question is whether its ratios fall inside our envelope or whether it demands a new one. If the object is natural but foreign, we should expect at least some compositional oddities. Different parent star systems have different protoplanetary disk temperatures, metallicities, and bombardment histories. Even the same chemistry can appear in different proportions. That is normal diversity. What would be abnormal is a chemical profile that looks deliberately constrained. For example, a coma dominated by refractory dust with an unusually weak volatile signal would be strange for a body bright enough to show a large coma at this distance. A rich set of volatiles with almost no apparent outgassing thrust would be equally strange. In other words, chemistry can cross-check dynamics. If the orbit says not enough outgassing, but the spectrum says outgassing should be strong, then the natural model is under pressure. If both orbit and chemistry agree, pressure eases. Current reports are mixed, partly because the data are still thin. Some teams see the expected CO-rich behavior at large heliocentric distances, indicating activity is being driven by super volatile ices rather than water. Others note that dust-to-gas ratios look high compared to typical solar system comets at similar distances. Neither point is unprecedented on its own. What matters is whether a coherent pattern emerges after the object moves closer and the spectral signal strengthens. The key is the transition zone. As 3I Atlas approaches the inner solar system, water sublimation should turn on and start dominating the coma. That is when gas production rates rise sharply, jets become more visible, and non-gravitational acceleration usually increases. If the water turn-on is delayed, weak or oddly distributed, that changes the dynamical expectations. If the water turn-on is normal and vigorous, then any organized acceleration becomes harder to explain without outgassing. Spectroscopy can also probe isotopes. The deuterium to hydrogen ratio in water, the carbon isotope ratios in CO and CN, and nitrogen isotopes in NH species have become powerful tools for tracing origin. Solar system comets span a range of DH values, but again within an envelope. An interstellar comet could fall outside that envelope in a natural way. If it does, it tells us about the environment it formed in. If it does not, that would be surprising in the opposite direction, because it would imply that chemical processing across star systems converges more tightly than we assumed. There is one subtlety here. A technological object could still mimic natural chemistry by carrying volatile coatings or dust. If someone wanted a probe to pass through another system quietly, embedding it in a comet-like body is a plausible strategy. That means chemistry alone cannot prove technology, but chemistry can still constrain it. A disguised probe would have to carry a coherent, sustained supply of volatiles to maintain a realistic coma through multiple thermal regimes. If the coma behaves chemically like a standard comet across the whole passage, that is a stronger natural argument. If chemistry is patchy, inconsistent, or energetically mismatched to observed brightness and thrust, that is where the disguised probe narrative gets more oxygen. This is also where the shadow story intersects again. If a solid structure is affecting the coma, it may alter local chemistry. The region behind a shadow could stay colder. Colder regions sublimate differently. That should show up as asymmetries in gas distribution or unexpected spatial variation in spectral lines. Spatially resolved spectroscopy is difficult but not impossible. Large telescopes can map emissions across the coma. If the wedge is real and physical, it should have a chemical footprint. The other chemical fingerprint is dust mineralogy. Infrared spectra of dust can reveal silicate features, carbonaceous grains, and crystalline versus amorphous structures. Solar system comets often show a mix, with crystalline silicates implying heating and processing close to the Sun early in their history. An interstellar object formed far from its star might show more amorphous material, if 3I Atlas shows an extreme dust signature, either unusually processed or unusually pristine, that would be a strong natural clue about its origin. But again, we have to think in coupled systems. Chemistry, dust, orbit, and morphology are all versions of the same underlying physics. It is easy to point to one odd ratio or one strange image and jump to a story. It is harder to find a story that satisfies all constraints simultaneously. That is why the coming perihelion phase matters so much. It strengthens every signal at once. More light means better images. More gas means stronger spectral lines. More outgassing means non-gravitational terms should become clearer. If the anomalies are artifacts of weak data, they will fade as signal-to-noise improves. If they are real, they will sharpen. There is also a human reason to care about the chemistry now rather than later. In a year, the object will be fading. Its best observing window is short. The spectrum you miss this season is gone. That is true for any interstellar visitor, but it is especially true here because the object is already unusual enough to demand a full inventory while we can still take one. So the next phase of the story is not just what happens at Jupiter. It is what happens to the coma's chemistry as the Sun takes over. If 3I Atlas behaves chemically like a comet should, we will be forced back toward natural explanations for its orbit and shadow, even if those explanations are new and uncomfortable. If it does not, then we are not just looking at a weird comet. We are looking at an interstellar object that refuses to sit inside our current model space, and that refusal will have to be explained with real physical mechanisms, not with vibes. Perihelion is where natural comets show their hand. It is the point of closest approach to the Sun, the moment when surface heating peaks, volatile layers erupt most strongly, and the coma becomes a real physical laboratory instead of a faint halo that can be argued over. For 3I Atlas, perihelion is also the last phase where the organized acceleration question can be tested at high signal, because after the peak the comet fades and measurement leverage drops. A normal comet approaching perihelion typically follows a recognizably smooth curve in brightness and gas production. Water sublimation rises steeply once the surface reaches the critical temperature regime. CO and CO2-driven activity gives way to H2O-driven activity. Jets become brighter and more structured, and the non-gravitational acceleration increases but in a way tied to the Sun-facing geometry. You can model this with rotating active patches, thermal lag, and uneven surface composition. The details vary, but the overall pattern is stable across hundreds of observed comets. The expectation for 3I Atlas, if it is natural, is a strong perihelion signature. Not necessarily a spectacular outburst, but a clear increase in gas production, especially water. That signature should be visible in spectra as stronger OH bands and water-related lines, and visible in imaging as a denser, brighter inner coma with more obvious dust jets. If those things happen, they provide an internal engine capable of explaining the orbit corrections without invoking anything beyond comet physics. But if perihelion comes and the signature is muted, the implications change. Suppose the comet brightens optically, meaning dust scattering rises, but water-related emission stays unexpectedly low. That would imply high dust-to-gas ratios with insufficient thrust from sublimation to match the observed non-gravitational acceleration. The natural model space shrinks. You then have to propose either a very unusual volatile mix that produces thrust efficiently without strong water lines, or a physical process we do not yet understand for interstellar bodies. The same logic applies to time variability. Outgassing that drives orbit changes should correlate with brightness fluctuations, because strong jets throw off dust as well as gas. Large unexplained course corrections without accompanying photometric or spectral changes are suspicious in a strictly physical sense. Conversely, if the comet displays sudden outbursts and orbital fits respond in sync, that favours a natural interpretation. Perihelion is also where the shadow can either dissolve into normal morphology or become harder to explain. Near peak heating, the coma thickens. The dust field becomes more isotropic. Turbulence rises. If the wedge is a void carved by jets, it should deform, rotate more quickly, or blur as competing jets switch on. If the wedge is a shadow cast by an opaque structure, two things should happen. Either the shadow remains coherent even as coma density increases, implying a structure stable enough to keep casting it, or the shadow shifts in a way consistent with controlled reorientation rather than chaotic gas flow. Both outcomes are diagnostically useful. There is also a mechanical fragility test. Natural comet nuclei are weak aggregates. Perihelion heating can induce cracking, surface collapse, and fragmentation. If the nucleus ruptures, you get either a slow mass loss event or a dramatic split into companion fragments. Those fragments typically acquire their own coma and drift apart along trajectories governed by outgassing and radiation pressure. If 3I Atlas fragments in a normal way, that is a strong natural marker. If it remains unusually coherent through thermal stress that should have fractured a loosely bound icy body, that coherence becomes part of the anomaly set. None of this is abstract. We have a decent analogue record. Comets that are dust-rich and gas-poor tend to show different perihelion curves and weaker non-gravitational signals. Comets with strong supervolatile activity far out often show a distinct handoff to water near 2 to 3 AU. Comets that are structurally fragile often betray that fragility near perihelion. These patterns are not perfect, but they are robust enough that deviation is informative. And because 3I Atlas is interstellar, deviation could mean two very different things. It could mean foreign but natural, a nucleus built differently, with a different layering of volatiles, altered by a different radiation history, maybe even processed by passing close to its home star in the past. Or it could mean not just foreign, that the mechanisms driving its behavior are not compositional at all, but functional. The honest way to separate these meanings is to measure whether any deviation can be explained by plausible interstellar comet formation paths. Formation paths provide a big natural toolbox. Some star systems are colder on average, allowing CO-rich bodies to form and persist with thick volatile mantles. Some are more metal-rich, producing dustier aggregates. Some have more violent early histories, creating collisional fragments that are structurally tougher. An interstellar comet can plausibly look outside our solar envelope without being anything other than a comet. But the toolbox is not infinite. You cannot get a strongly organized anti-sunward acceleration pattern without enough mass flow in the correct direction. You cannot sustain a clean geometric shadow through intense perihelion turbulence without a stable physical cause. You cannot keep the orbit converging toward a narrow targeting corridor while your jet physics becomes more chaotic. If perihelion observations show those three things together, you have a coupled anomaly that a single formation story would struggle to cover. This is why perihelion season is not a side chapter. It is the phase that either collapses the mystery or hardens it. If the data become boring in the expected way, the object becomes a valuable but natural interstellar comet. If the data become boring in the wrong way, muted activity with organized acceleration, stable shadow through turbulence, then even a cautious scientific community is forced to consider new categories. Whatever the outcome, perihelion gives us a clean dividing line. After it, the comet will cool, activity will fade, and the system will drift back toward ambiguity. So this is the moment where observers have to be relentless. Multi-band imaging, repeated high-precision astrometry, spectroscopy across volatiles, infrared dust mineralogy, and polarimetry. If these constraints are collected now, the debate ends up anchored in measurable physics rather than in whichever story spreads fastest online. And that brings the narrative to the next step. Once perihelion passes, we can compare the pre- and post-peak behavior in a way that removes many degeneracies. Is the acceleration symmetric around perihelion as thermal models predict? Does the shadow evolve with phase angle the way a void model demands? Do spectral ratios follow the standard volatile handoff, or do they remain oddly constrained? Those comparisons are where the final shape of this object's explanation will emerge. Once perihelion is behind us, the question is no longer what might be happening, but what actually happened when conditions were strongest. Post-perihelion behavior is the cleanest mirror we get in comet science. It lets us compare the object against itself under two opposite thermal regimes. If the earlier anomalies were caused by observational weakness or processing quirks, they should weaken as the coma thins and the geometry simplifies. If they were caused by a real physical driver, they should leave a consistent dynamical and morphological trail even as the comet cools. For a natural comet, the script after perihelion is familiar. Gas production falls with distance, water lines fade first, supervolatile lines fade later, and dust emission gradually settles into broader fans. Non-gravitational acceleration drops because the engine of sublimation is shutting down, and any residual thrust becomes more erratic as active patches wink out unevenly. That decline is not perfectly smooth, but over weeks it trends in the same direction in almost every well-observed comet. So here is the simplest post-perihelion test. If 3I Atlas keeps showing a coherent, strategically aligned acceleration while its spectral activity fades in the normal way, that breaks the thermal link we rely on to explain comet push. Even a weird interstellar volatile mix cannot keep producing thrust in the same direction once the heating regime changes, unless there is a non-thermal driver doing the work. If instead the acceleration falls and becomes noisy in step with declining activity, then what looked organized earlier was likely a fragile inference from early data. The second test is symmetry. Thermal models predict that outgassing peaks slightly after perihelion because of heat stored in subsurface layers, then decays. That creates a mild asymmetry, but the overall thrust pattern on the inbound leg should resemble the outbound leg when plotted against solar distance. If you rebuild the orbit using only post-perihelion astrometry, and the thrust terms you infer do not match the pre-perihelion ones at the same distances, that mismatch demands either a major change in surface activity or a different forcing mechanism. In a normal comet, such a dramatic forcing flip is rare unless fragmentation or a large outburst has occurred. This symmetry logic applies to the shadow too. After perihelion, the coma becomes less dense. Contrast improves. If the wedge was an artifact of heavy stretching, its stability should disappear as the signal simplifies. If the wedge was a jet-carved void, it should evolve with changing phase angle and with the retreat of active regions, gradually rotating or blurring into standard fan structures. A shadow cast by a solid element is different. It should remain tied to a specific orientation or pivot in a way that tracks a rigid driver. Even if it weakens, the geometry of its evolution matters more than its darkness. There is a third post-perihelion discriminator that is easy to miss because it lives in the dust. Dust grains do not fly straight. Their trajectories depend on size and on radiation pressure. When activity is intense, you get a dense mix of sizes and chaotic patterns. After perihelion, as production falls, dust tails stratify. Large grains form a heavier, narrower tail. Small grains disperse into a broader sheet. If we see a persistent evacuated wedge slicing cleanly through that stratified dust field, it gets harder to attribute it to random jet geometry because the stratification itself is an average-out process. A void created by short-lived jets should wash out as the dust size distribution settles. At this stage, you might ask why all this emphasis on tests is necessary. Why not just accept the simplest story and move on? Because simplified stories have a way of surviving long after they should be dead. If 3i Atlas turns out to be natural, the responsible outcome is not mystery solved, but which natural model wins and why. The first 3 interstellar objects have already shown us that they do not line up neatly with expectations, and that the cost of premature certainty is high. The only way to avoid repeating the same argument loop for a decade is to lock the answer to constraints while we are still watching the object. There is also a practical reason to be strict. Comet modelling is about coupled phenomena. 1 anomaly can be a fluke, 2 can be coincidence, 3 that persist across perihelion and into the outbound leg become a system. A system is what physical theory needs in order to be refined. If the orbit stays organized, the shadow stays geometric, and the chemistry stays energetically mismatched, then even the most conservative interpretation becomes, we need a new category of interstellar comet behavior. It doesn't require a leap to technology. It requires a commitment to expanding natural model space in a way that explains all 3 constraints at once. If, on the other hand, 1 or more anomalies dissolve, that is not a failure. It is the most valuable kind of negative result. It tells us which parts of the early story were products of thin data, human pattern making, or over-aggressive processing. In astronomy, negative results are often what save you from spending years chasing a ghost. The final layer after perihelion is trajectory forecasting. Once the outbound orbit stabilizes in the fits, we can calculate long-term dynamical futures with confidence. Is the object definitively leaving on a hyperbolic path? Is it loosely captured? Is it in resonance? Is it in a temporary quasi-satellite state? Those outcomes are not philosophical. They are numbers with uncertainties, and once those uncertainties shrink, whole families of explanations vanish. A clean escape with normal thrust terms leaves only the natural toolbox on the table. A bound or near-bound outcome with thrust coherence multiplies the questions. And then there is the simplest truth that tends to get lost in the noise. Regardless of what 3I Atlas is, it is an interstellar sample we did not expect to get this soon. Even if every anomaly collapses into comet physics, it will still widen our understanding of what other star systems produce. If any anomaly survives, the object becomes more than a sample. It becomes a boundary case for the way we define natural bodies in the galaxy. Either way, this is not a distraction from science. It is science happening in public, under pressure, at the exact time when the data still exists to settle it. At some point, the discussion stops being about a single comet and turns into a question about our high sample of interstellar visitors as a whole. 3 objects is not enough to define a population, but it is enough to create a pattern in the human mind. The first interstellar object, Oumuamua, looked geometrically extreme and showed non-gravitational acceleration that was hard to tie to obvious outgassing. The second, 2I Borisov, behaved like a comet but carried chemistry outside our solar system envelope. Now 3I Atlas arrives with a persistent shadow in its coma and an orbit that some models call statistically too useful for Jupiter braking. If you line that up, it feels like a trend. The danger is that it might be a trend made by our own selection. Selection bias is the most prosaic way to deflate an extraordinary story, and because it is prosaic, it is also powerful. We do not detect all interstellar objects. We detect the ones that are bright enough, close enough, and slow enough to track. Interstellar space could be full of small, dark, fast bodies that pass through undetected. What we see are the outliers. If that is true, then of course the ones we detect look unusual. Their unusualness is precisely what makes them detectable. A weird brightness curve, an unusually active coma, a trajectory that happens to spend more time in our survey volume. Those are all ways a visitor can rise above the noise. That argument explains a lot. It explains why our first few detections might cluster in the strange tail of the distribution. It also explains why probability estimates based on random arrivals can feel unstable. If interstellar objects are not random in practice, because we only see a biased subset, then calculating how unlikely a particular orbit is becomes a fragile exercise. The orbit could be rare among all arrivals and still common among detectable arrivals. In that case, a 1 in 20,000 inbound geometry is not a warning sign. It is just what a detectable interstellar visitor looks like. But selection bias has limits. It can tell you that you should expect weird objects to be overrepresented. What it cannot easily tell you is why the specific weirdnesses seem to fall into different categories. Detectability can make you favour brighter comets and larger bodies. It does not by itself tell you why one object should be weird in shape, another in chemistry, and a third in orbit and internal morphology. That is where people who take the anomaly seriously say the bias shield has a hole. Even if we are sampling only outliers, the outliers still look oddly specialized. There is a deeper version of that concern, and it is the point where the narrative gets uncomfortable in a different way. If these objects are not random, what are they? One possibility is that the galaxy produces streams of debris that travel on preferred paths. Stellar systems move through the Milky Way in organized flows. Clouds of dust and small bodies can be ejected during planet formation, and over time those ejecta need not fill space uniformly. If our solar system happens to intersect a debris stream, then interstellar visitors could arrive in correlated directions and with correlated energies. In that setting, an orbit that looks designed under isotropic assumptions might be normal under stream assumptions. Another possibility is more psychological than physical. We are misreading coincidence as intention because we are primed to do so. Once a community has lived through a decade of debate about artificial probes after Oumuamua, the third arrival does not enter a neutral landscape. It enters a landscape full of expectation. That expectation shapes what we look for and how we interpret it. People push contrast harder, hunt for shadows, run specific trajectory tests, and the moment something odd appears, it is framed inside the old argument. In that sense, the pattern is not in the objects, it is in the conversation around the objects. Still, there is a reason the deliberate probe idea keeps resurfacing, and it is not just internet drama. From a purely engineering standpoint, a comet makes a plausible disguise. A natural comet is expected to appear suddenly. It naturally produces a coma that hides its nucleus. It naturally experiences non-gravitational forces that complicate orbit fits. If you wanted an interstellar craft to pass through another system without shouting, you could do worse than to embed it in volatiles and let it behave mostly like a comet. The camouflage would be passive. You would not have to fake data. You would just let the real comet physics obscure the core. This is where some researchers invoke a science fiction concept called the dark forest hypothesis. The claim is not that the dark forest is true. The claim is that if a galaxy contains multiple civilizations, it is rational for them to remain quiet, because broadcasting your location could be dangerous. In that world, probes become the safer way to explore. You do not send a loud signal. You send something that watches. And if you send something that watches, you want it to blend in. Again, as a motive story, this is speculative. But as a motive story, it is consistent with the engineering reality that unannounced scouting is a rational strategy in an unknown environment. Notice where this lands us scientifically. You cannot prove a motive theory with orbital mechanics. But motive theories shape the kinds of physical signatures people think to test. If a probe were disguised as a comet, you would expect its abnormalities to be subtle, not theatrical. You would expect them to show up as small mismatches between different data sets. An acceleration too coherent for the visible outgassing, a shadow too geometric for the local turbulence, a thermal profile too constrained for its brightness. That is exactly the kind of mismatch bundle people believe they are seeing in 3i Atlas. It does not prove anything, but it explains why the story feels internally consistent to those who are already willing to consider the technological hypothesis. Now flip the framing back to a strict natural view, because that is where science has to live if it wants to stay honest. Interstellar objects are not coming from somewhere. They are coming from many different star systems with many different histories. Some were expelled early, some late. Some were cooked under high radiation stars. Some preserved in cold disks. Some are fragments of larger bodies. Some are primordial aggregates. If you randomly sample 3 objects from that enormous diversity, it would actually be surprising if all 3 looked normal by solar system standards. The expectation for the first few arrivals is not sameness, it is variety. That natural diversity argument is the cleanest way to interpret the sequence without reaching for intent. The first object was structurally weird because we happened to catch a fragment or an extreme shape. The second was chemically weird because it formed colder or in a disk with different ratios. The third looks morphologically and dynamically weird because it has a different layering of volatiles, a different dust size distribution, or a different nucleus geometry that creates stable low-density fans. In other words, the pattern is not 3 artificial probes. The pattern is 3 reminders that our solar system baseline is not universal. If that is the right story, then the job is to expand our natural model space until these objects fit without forcing. That does not mean inventing ad hoc excuses. It means doing what astronomy always does when it meets something new: measure tightly, simulate broadly, and accept that the galaxy may build things differently from the way our local neighborhood did. So where does that leave us with 3i Atlas specifically? It leaves us in a place where we should be careful about narratives and ruthless about constraints. Selection bias might explain why we see weird things first. It does not explain the specific coupled anomalies unless we can show that those anomalies naturally co-occur in interstellar comet physics. Dark forest motives might explain why a disguised probe is plausible. They do not matter unless the physics stays stubbornly beyond natural models even after perihelion and the Jupiter encounter. This is why the next step is not another round of probability arguments or another viral image. The next step is to ask a concrete question with a concrete answer. After the dust settles and the orbit is locked, does 3i Atlas behave like a natural interstellar comet with unfamiliar parameters, or does it keep forcing mismatches across orbit, morphology, and chemistry that require a fundamentally different kind of driver? If it is the former, the story does not get less interesting. It gets more useful because it teaches us what other systems build. If it is the latter, then we have crossed a boundary in a way that no amount of storytelling can erase, and the category of explanation will have to widen, whether we like it or not. After the flyby in perihelion season, there is a final, unavoidable phase that determines how this story will be remembered: consolidation. This is when separate streams of evidence stop being treated like parallel rumours and get welded into a single physical model. It is also when the early noise either collapses into standard comet behaviour or refuses to do so. The first consolidation tool is an updated orbital solution built from the full arc of astrometry. Early in a comet's apparition, orbit fits are elastic. Small positional errors, gaps in coverage, or unmodelled outgassing can push the inferred path around. once the object has passed perihelion and Jupiter's neighbourhood, that elasticity vanishes. The trajectory either settles into a clean hyperbolic escape with well-behaved non-gravitational terms, or it does not. That outcome is one of the hardest constraints to argue with because it is geometric, not interpretive. If the final outbound orbit is strongly hyperbolic, with excess speed clearly above zero and thrust terms that fade in step with declining activity, then the organized approach narrative loses its anchor. Some formation models might still be challenged by the shadow or chemistry, but the core mechanical claim targeting a braking corridor would not survive. At that point, the most productive scientific framing becomes clear. 3I Ice Atlas was a natural interstellar comet with an unusual internal morphology, and our job is to explain that morphology inside an expanded natural model space. If the outbound orbit is near parabolic or bound, the situation flips. Capture is not impossible in nature, but it is rare for interstellar arrivals. Captures that happen naturally tend to be temporary and messy. In numerical swarms, you would see a wide spread of post-encounter outcomes. If instead the solutions converge tightly toward a specific bound family, then the orbit itself becomes a behavioral signature. Not a proof of technology, but a proof that some coherent driver acted to select a narrow dynamical niche. The second consolidation tool is a coupled activity thrust model. This is where comet physics becomes quantitative. You take the measured gas production rates, dust emission, rotation state if available, and thermal lag estimates, then ask a simple question. Can these parameters supply the impulse required by the non-gravitational acceleration terms? In ordinary comets, the answer is yes to first order, and the residual mismatches can be explained by geometry and local jets. If the answer for 3I Atlas is no by a wide margin, then either the activity estimates are wrong or the thrust is not coming from sublimation. There is no third option. This is also where any camouflage by comet idea becomes falsifiable. A disguised probe could, in principle, carry volatiles, but it would still have to satisfy energy accounting. If the thrust budget does not match the volatile loss budget, then something non-thermal is pushing. If it matches well, the disguised probe hypothesis becomes unnecessary, even if the object remains visually weird. The third consolidation tool is morphology tracked through geometry. The wedge shadow debate cannot be settled by a single dramatic stack. It is settled by evolution. You line up images across time, across phase angles, and across wavelengths. A jet-carved void should evolve with rotation and fade as activity reorganizes. A physical shadow cast by a solid element should keep a coherent relationship to the nucleus and to solar illumination. Even if its darkness weakens with a thinner coma, its geometry should not behave like turbulent dust flow. This evolutionary test is especially powerful because it is insensitive to the emotion of the debate. A compressor artifact does not persist coherently across different telescopes and reductions. A projection artifact does not stay aligned through large geometry swings. Physical causes do. If the wedge dissolves into normal fan morphology once the coma thins, that becomes a clean natural result. If the wedge persists, keeps sharp boundaries and evolves in a mechanically consistent way rather than a turbulent way, then it remains an anomaly even in the strongest data phase. At that point, the remaining question is not, is it real, but what physical structure can create it? The fourth consolidation tool is chemistry under the full thermal cycle. By now, spectra should cover the super volatile to water transition on the inbound leg and the fade out on the outbound leg. Ratios can be compared against both solar system envelopes and plausible interstellar formation envelopes. If the composition stays coherent and energetically consistent with observed brightness and thrust, then chemistry supports the natural model. If it stays odd in a way that conflicts with thrust or brightness, and stays odd symmetrically pre- and post-perihelion, then chemistry becomes part of the coupled anomaly set. At this stage, scientific debate becomes a filtering process. Many early narratives will die quietly because they require things that no longer fit the final constraints. Others will survive, but in a downgraded form, reinterpreted as natural extremes rather than as evidence of control. That's how healthy science works. It shrinks the space of stories until the remaining ones line up with numbers. There is also a quiet but important institutional reality here. Consolidation is when teams publish the definitive papers, and that is where a long-running controversy can either be defused responsibly or inflamed for years. If the final outputs are clear about uncertainties, report full covariance, and show that multiple independent instruments agree, then the community can converge even if it doesn't love the conclusion. If the final outputs are vague, incomplete, or selectively reported, then the controversy persists because the data never get a stable home. So the real finish line is not a headline. It is a consistent model that satisfies 4 demands at once: trajectory, thrust budget, morphology evolution, and chemistry. If a single natural model can satisfy all 4, then 3D Atlas becomes a landmark case in interstellar comet physics, not a boundary case for technology. If no natural model satisfies all 4, then the conversation widens, regardless of how uncomfortable that widening is. That is why the story matters even if the extraordinary version fails. If 3i Atlas turns out to be natural, we still learn that 3 interstellar objects have arrived with 3 different kinds of extremes, and that tells us something about the galaxy's inventory. If any coupled anomaly survives consolidation, we learn something even bigger: that our observational category, comet, may not be broad enough to cover all the ways small bodies can move and behave between stars. Either way, when this season ends, we will not be left with a mystery kept alive by grainy images and probability arguments. We will be left with a constrained set of physical facts that say what 3i Atlas did, how it did it, and what kinds of objects can plausibly do the same thing. From there, the final judgment is not an act of belief. It is a choice between models that fit and models that do not.